The second part of the fundamental theorem of calculus actually is providing a method to find integrals without having to evaluate limits or to find a ton of rectangles to use an estimate of the area under the curve, and it has to do with antiderivatives from section 4.9. So what it says is, if I'm trying to find the area under f between a and b, the only thing I have to do is find an antiderivative of f and evaluate the antiderivative of f at b and subtract it by the antiderivative evaluated at a. Now, you do have to respect the order in which this appears. For example, if I have the integral between 1 and 5 of some function, remember that I'm calling it f of x dx. I could have called it f of t dt, f of h dh, or anything like that. This is just an independent variable. So antiderivative of f, remember that we are calling it capital F, evaluated at 5 minus capital F evaluated at 1. If you're switching the order, then this integral will be wrong. But all the other properties that we have learned for the definite integral apply. For example, if instead of this I'm trying to find the integral between 5 and 1 of f of x dx, then this is just simply negative of the derivative of 1 through 5 of f of x dx. Remember that all the other properties that we've seen apply. So if this is out of order, then you can change the order of the limits of the integral by just adding a negative sign, because it will be the opposite of that. But for the most part, if everything is in order, then this is the order that this should follow on. And notice that if I'm doing this, this will say, well, this will be the antiderivative of 1 minus the antiderivative evaluated at 5. And this is exactly what this is, because if I do this, this will be antiderivative of 5 minus antiderivative at x equals 1. But the opposite of it will be actually this. So this is the order. This upper limit is evaluated first, and this lower limit is evaluated second. Now you're dying to get to this part because you want to see how they look like in an exercise. So example 5, the directions will say evaluate the integral. So you notice how we have lower and upper limit, and we actually have a function to find the integral of. So remember, this function is e to the x, goes through the point 0, 1. So I'm trying to find the area between 1 and 3. Now this area has no formula, therefore thank God I know calculus, I can apply integrals. So the theorem says that you can find any antiderivative. So I know that if my function is e to the x, one antiderivative is e to the x, and in general all of them will look like this, e to the x plus c. Since it says any antiderivative, so I'm gonna pick the simplest one that doesn't have a constant. Now I'm gonna show you how, let's say that I do want a constant. Let's say that my antiderivative is e to the x plus 5. You're gonna see that it doesn't matter if it's 5 or 10 or 15, the answer will always be the same. Okay, so let me do with the simplest one as they recommend, and then let me do it with this one just to show you that it's the same thing, so why bother? So no cherry on top this time. Okay, so using the fundamental theorem of calculus part 2, this says this will be the antiderivative evaluated at 3 minus the antiderivative evaluated at 1. The antiderivative, I'm going to pick the simplest one, e to the x, so this will be e to the third minus e to the 1, which is e to the third minus e. You can factor this if you want, but then that's as far as you can go. So that's the answer. Now let's say that I want to use, instead of the simplest one, let me use this one. So it would be e to the third plus 5 minus antiderivative evaluated at 1, it would be e to the 1 plus 5. So this would be e to the third plus 5 minus e to the 1, well, which is e, I'm just going to call it e, minus 5. You see how the constants, in any way, they are going to end up canceling each other. So therefore, this is e to the third minus e, which is exactly what I have before. So it doesn't matter what antiderivative I'm using, but I'm just going to stick with the simplest one because I know the constants will cancel out. Now example 6 says find the area under the parabola y equals x squared from 0 to 1. Now they don't give me an integral. They don't even suggest that I use the integral, but I have to know that I have to use the integral whenever they ask me for area under some curve. So I know that I have to find the integral between 0 and 1 of x squared. Don't forget the dx. If you don't write dx, then this will be wrong. It's like speaking Spanish and forgetting the ito. Okay, a joke. Anyhow, you know that this, from a previous section, the answer was 1/3. So let's see if we get 1/3 applying the second part of the FTC, Fundamental Theorem of Calculus. Come on, people. Okay, so the antiderivative of x squared is x to the third over 3. And now I'm going to evaluate it between 0 and 1. Some books use the following notation. This is what I use. You may use a bracket. I use just simply a line. So this is just to say I'm going to evaluate this function between 0 and 1. You can see in some other books that they write x equals 0 to 1. So either way, it is the same. Whoever is correcting your work is going to understand the same idea. This will replace the antiderivative evaluated at 1 minus antiderivative evaluated at 0. This notation will replace this. This I like it better than this. Also because not always the antiderivative, we will call it capital F, we will call it different names, so why bother sticking with one name? This is just notation. Okay, so now when x is 1, I have 1 cubed, which is 1/3, minus 0 cubed over 3. And that is simply 1/3, which is exactly the same as what we had before. Not only that, but there is also something I want to show you. If this is y equals x squared, you know the area is going to be a positive number because the function is positive between 0 and 1. So just keep that in mind. If the function is above the x-axis, then your answer, you know, is going to be positive. Now in example 7, it says evaluate this function. Now this function, this is just the same as having the integral between 3 and 6 of 1 over x dx. Now remember that when you are integrating, the function has to be continuous between 3 and 6, close. So you know that this function looks like this, and you're integrating between 3 and 6, so there's no problem, you can find the area. You will not be able to find the area if you are integrating between, I don't know, -5 to 6, because if you're going over the 0, then this function is not integrable if you include 0 in here. So between 3 to 6, you're safe, you can find the integral, and it's going to be an answer. So again, what is the antiderivative of 1 over x? We know that it's natural log of absolute value of x between 3 and 6. But you know that if x is between 3 and 6, then you know that the absolute value is itself. Because absolute value of 3 is 3, absolute value of 6 is 6. So you know the x's are positive. So this is just simply natural log of x between 3 and 6. So now the exact answer, unless they ask you for some particular rounding, you should not round. This is natural log of 6 minus natural log of 3, which is applying our properties of logarithms. You know that the difference of exponents came from division, so this can be merged into one natural log of the division of 6 by 3, which is natural log of 2. So this is our exact answer. You have to pay attention to rounding. depending on the problem, but this would be the end. Now the next problem we have finding the area of the cosine curve. So just to have an idea, remember cosine of 0 is 1 and cosine of pi over 2 is 0. So you're finding the area from 0 to some number b. You don't know what b is, but at least you know that b is between 0 and pi over 2. So you know that that particular function is going to be a positive function because the area between 0 and pi over 2 is above the x-axis, so that's going to be a positive number. So using part 2 again, the area between 0 and b of cosine of x dx is the antiderivative of cosine, which is positive sign, please, positive sign. I'm not saying the derivative, but the antiderivative is positive sign evaluated from 0 to b. And this is sine of b minus sine of 0, and this is simply sine of b. And that's all. Now, example 9 says, what is wrong with finding this area? So you have integral between -1 and 3 of 1 over x squared dx. You know that this is written as x to the -2, so the antiderivative will be x to the -1 over that exponent -1, evaluated from -1 to 3, which is, let me just rewrite this in a friendlier way. This is the opposite of 1 over x. So evaluating 3 here, I have -1/3 minus -1 over -1. This is +1, so this will give me -4/3. And what is wrong with it? And there is really nothing wrong. I mean, in terms of the operations, everything has been worked out the way it's supposed to be. However, the only thing that you haven't thought about is that, remember, 1 over x looks like this, but 1 over x squared looks like that, and the function is not defined when x is 0. So integrating from -1 to 3 really has no meaning, because this is an area that cannot be bound. I cannot integrate all the way to infinity, because these rectangles are going to have a height that is infinite. So I can never ever put a cap on how many infinities I'm adding. So this is not integrable between -1 and 3. So if the function is not integrable in the closed interval -1 and 3, everything that we have learned does not apply. So that's the only reason why this is wrong. But in terms of the calculations and the numbers and placing them and multiplying, everything is fine. I mean, everything is fine, but the fact that you are evaluating over a closed domain in which the function is not defined for one of the elements, then that makes everything else invalid. Okay, so let's just summarize the two parts. We have if a function is the area so far, then the derivative of that area function is the function itself. And we also have that if we're trying to find the area under the curve between two values, then that is just simply the difference of the antiderivative evaluated at those two, when the function is any antiderivative. So we're going to pick the easiest one. Now, if you see part 1 written in this way, you can say the following. If you have a function that is integrated and then differentiated, then because these two processes work as inverses, you have the function that you started with. And now the other part, then we can say similarly in the other order. If you have a function and then you are taking the derivative, okay, you're differentiating it, and then you are integrating that result, then what you have is the original, but not the original in general, the original in the form of the difference between those two values that you did the integral for. So the main idea of this section is that differentiation and integration are inverses. So one of them undoes what the other has done. Yay!